to measure integration and renal analysis. My name is Sunday Oluwafemi, and then today we will continue with the solution of exercises of session 1A of measure integration and renal analysis by Sheldon Axley. So in this video we will try to solve the last three questions, which is on question 12 to question 14. Okay, so question 12 now. Question 12. We have suppose f a comma b, how is Riemann integrable? So we have to prove that mod of f is also Riemann integrable. And that the mod of h to b of f is less than a of b. Okay, so there are many ways to prove this, but I'm going to approach this by the properties of supremum and then infimum. Alright, so first, by the hypothesis, we assume f is Riemann integrable. So that implies for any epsilon greater than 0, there exists a partition. Partition P shows that the upper Riemann sum, the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. So now let's define the upper Riemann sum of the mode f a comma b. So this will be equals to summation using the same partition summation j equals to 1 to n and then sj minus 1 s minus sj minus 1, then the submode of f sj minus 1 common sj. So by the properties of supremum, this guy will be less than or equal to summation j equals to n sj minus sj minus 1, the sup of this guy is sum of f. So this is just by the properties of the supremum. My properties of supremum. So, and then we can also, and then this is the definition of the UF a comma b. Okay. Okay, we can still extend this part with the odd. If we extend this part, then we can still extend this to be less than summation j equals to n is j minus this guy is always positive. The difference of our sub intervals are always positive, so this is the odds, and this is the same thing as mode of the upper Riemann sum. So we have that. So similarly, that is so long, sorry for that. So similarly, for the lower Riemann sum, we also have this condition. The infimum of f is j minus 1 sj. This will be greater than j equals to 1 to n, and sj minus 1. The infimum of f is j, so this should be sj, okay, sj minus 1 sj, and then the greater than or j equal to summation j equals to 1 to n sj minus 1 infimum of f of sj minus 1 and sj. The mode, and this goes to the mode of the lower Riemann sum. Okay, so by these two properties, combine them together, then you have u of u mod f a comma b of p minus mod f a comma b of p to be less than or equals to the mod of f a comma b comma what that's p minus n f a comma b plus p. Okay, and then this is less than or equals to external by since f is Riemann integrable, then the mode of this guy also should be less than or equals to 0, since this will be mode of externum, and externum is already always greater than 0, then this should be also less than externum. So thus mode f is Riemann integrable. Then also we can now show that the upper bound of this guy is lower than this other guy. So next, I want to show that the mode h to b of f is less than the mode of h to b of f. So here we can just using Riemann sum. We know that integral h to b of f is the limit mod p tends to 0 summation j equals to 1 to n xj minus sj minus 1 f of sj minus 1. So these definitions of Riemann Riemann sum. So the idea is that we have a partition P. So as we continue to refine the partition, then the sum, the Riemann sum, we actually approximate and give us the accurate area under the function f. So then let's define our Riemann sum. Let x of f comma p be our Riemann sum. J equals to 1 to n sj minus sj minus 1 f of, so let's just define it for f of ci, and then change of x. Let's leave it as xj minus 1 minus sj. It should be sj minus sj minus 1, where ci is any sub-interval of partition P. So by the properties of absolute value, we take the mode of xf of p, that is equals to the mode of j equals to 1 to n f of ci sj minus sj minus 1, and that will be less than or equals to summation j equals to 1 to n, then f ci sj minus sj minus 1, right? And this is less than or equals to j equals to 1 to n, since our sj minus sj minus 1 will always be positive, and then our function also is greater than or equals to 0. So we have fci. So then if we now take the limit, so as mod p tends to 0, then we have our integral h to b of f mod, that is equals to the mod limit mod p tends to 0 of x f of p, and that's less than or equals to integral h to b of f limit mod p tends to 0, and this is equals to limit mod p tends to 0 of j equals to 1 to n xj minus sj minus 1 mod f of ci. So, and then that completes the proof. So let's check the next question. Next question 13. We have suppose a comma b r is an increasing function meaning that c comma d belongs to a comma b. It's less than d implies f of c less than f of d. So you have to prove that f is Riemann integrable on A, B. So then let's start our proof. So let's define our P proof. Let's partition P equals to x naught x1 dot xn, and then we divide this to be an equal interval where xi equals to a plus ib minus a over n, that is for I equals to 0, 1, dot n. So that means that we divide our A to B into equal sub interval. So with that, then I define our supremum for each interval. So for each sub interval, our supremum of f of x for x belongs to xj minus 1 xj will be equals to f of x j. So let me use I. For xi. So why, since this holds since f of x, f is increasing. So since f is increasing, then your supremum will always be the last, will always be the end point of the sub interval. So also the infimum of f of x for x belong to xi minus 1 xi, the infimum also will be xi minus 1. The same condition since f is increasing. Okay, that means that the upper Riemann sum and the lower Riemann sum will be equals to summation j equals to I equals to 1 to n, and then the difference xi minus 1 into bracket f of xi minus f of xi minus 1. That just by the definition. And then since we divide our intervals to be equal, that means that the summation I equals to 1 to n of this interval will be b minus a over n. So we are left with this f of xi minus f of xi minus a. So then due to telescoping sum, this is also equals to fb minus f of a due to telescoping sum. So we have that. So now we can choose our n. We can choose n large enough such that b minus a fb minus f of a over n will be less than epsilon to construct an appropriate partition. Okay, with that we can conclude that UF a comma b of b minus n f a comma b is less than epsilon, and hence f is Riemann integrable. Okay, so let's check the last problem. We have question 14. This is quite long. Let's add, suppose we have a sequence of Riemann integrable function. Is a sequence of Riemann integrable function on the same interval a comma b, and then such that f1 f2 they are converges uniformly, and a comma b to a function f a comma b to r. So you have to prove that f, the function that converges to, is Riemann integrable. And then let's show that integral h to b f is equal to limit n tends to infinity integral ab fn. Okay, so let's start the proof. So since our fn's are Riemann integrable, then for any epsilon greater than 0, since fn is Riemann integrable by the hypothesis, so for each n there exists a partition P such that the difference between the upper Riemann sum and then the lower Riemann sum is less than epsilon over 3. Okay, so and also from the hypothesis we have fn converges to f. So say since f of n converges uniformly to f, lambda there exists, by the definition there exists an n such that for all n greater than n, the difference between f of n and f can be made very small, epsilon over 3b minus a, for all x that belongs to a, comma b. So that's just by the definition. So now let's relate everything together. So since this holds, That means that for any partition P, since f of n converges to f, that means that the difference between the upper Riemann sum and then the lower Riemann sum, the upper Riemann sum of the function f, this difference between these two guys will also be less than epsilon over 3. Okay, and then the same thing for the lower Riemann sum, the difference between these two guys, the sequence and this will also be less than epsilon over 3. So we can now apply the triangle inequality. So the upper Riemann sum of u a comma b minus the lower Riemann sum of a comma b, so that will be less than mod u of f comma b minus u of fn. So let me include the interval a comma b u fn a comma b plus u of fn a comma b comma p minus n of fn a comma b of p, and then lastly plus the u of the lower n of fn comma a p e minus n of f a comma b p. Okay, and all this is less than epsilon because this is less than less than epsilon over 3. This is also less than epsilon over 3. This also less than epsilon over 3. So we sum everything together, then we have all of them is less than epsilon. So that proved that so that shows that our f is Riemann integral. So next we need to show that integral ab of f equals to limit n tends to infinity integral ab of f of n. So we already should have given epsilon greater than 0 by uniform convergence. There exists n, shows that for all n greater than or equals to n, f of n of x minus f of x is less than epsilon over 2b minus a for all x that belongs to a comma b. Therefore, the mode of our f of n integral ab fn of x minus integral ab of x is less than or equal to integral ab mode of fn of x minus f of x, and this is also, let's say, less than integral a integral ab epsilon over 2p minus a and this equals to Sn over 2b minus a, then b minus a, and this equals to Sn over 2. So then limit n tends to infinity, integral ab fn of x is equals to integral ab f of x. That end that proof. So that end all the exercises in section 1a. In our next class, we'll be going to do this section 2a of the textbook we are using. Hope to see you there. Don't forget to subscribe and share with fellow graduate math students. Thank you. See you.